All right, let's move forward and do example 2. Okay, here we go. A study is done to determine if company A retains its workers longer than company B. All right, pretty standard, straightforward study, sounds to me. Company A samples 15 workers and their average time with the company is 5 years with a standard deviation of 1.2. Notice that standard deviation is the sample standard deviation, not the population, okay? Company B samples 20 workers and their average time with the company is 4.5 years with a standard deviation of 0.8. Okay, assume the populations are normally distributed. Okay, I like that. So central limit theorem is already satisfied because as I was reading that, I noticed that those sample sizes were less than 30. Okay, but we're good to go because the populations are normally distributed. Conduct an appropriate hypothesis test at the 5% significance level. All right, so in the past, I think I was writing down the null and alternative hypothesis first with the claim and all of that kind of stuff. But since we have so much information now with 2 separate samples, I'm going to start by just writing down all of the different information about the samples. Okay, so 2 separate samples, and it's a really good idea to label them. And it's kind of up to you with how you want to label them. But I'm going to go ahead and just say, all right, company A. I'm going to let this be my sample number 1. Okay, so company A, I want to list all of the information about that sample. Okay, so first of all, I'm going to say that we're going to be talking about population mean number 1. Okay, sometimes you might want to say like a little subscript A on there if you want to, but I'm going to use the subscript 1 and to keep everything consistent with the way that the test statistic is written. So like up here, this test statistic all has like subscript 1 and subscript 2, depending on which sample you're talking about. So I'm going to go ahead and just tell myself right now that I'm making company A, I'm making that sample number 1. So you could use a little subscript mu sub A if you want, but I'm just going to keep track. Okay, so mu sub 1, and we don't know what that is. So I'm just going to say that that's going to be designated as mu sub 1. But we do have a sample of 15 workers. So that would be like N1. The sample size is 15. Okay, their average, okay, mean time is 5 years. So that's going to be X1 bar. The sample mean is 5. And then the standard deviation is 1.2. So I'll say S1. Sample standard deviation is 1.2. Okay, and then for company B, I'm going to let that one be sample number 2. So I'm going to say that that's mu2 for its population mean. And then its sample, okay, company B samples 20 workers. So that's N2 is 20. Their average time was 4.5. So that is X2 bar is 4.5. And then its standard deviation, S2, equals 0.8. All right. So that's all of the relevant information that we wanted to write down right at the beginning. Let's go ahead and write down that significance level as well. So I'll just make a note to myself real quick that we have alpha is 0.05, and we do have that we have a normal. Normality is given. Because I do want to do that normal check. If normality is not given, then we need both of these samples to be bigger than 30. Okay, so let's go ahead and write down the alternative hypothesis, which is, or the null and the alternative hypothesis. We have to understand in the context of the situation. So for this, we're just trying to see if there is some kind of a difference. Maybe it's a not equal to, maybe it's a greater than, maybe it's a less than. But for the null hypothesis, we're always just going to assume in these types of hypothesis tests that mu1 equals mu2. Okay, and we're familiar with the null hypothesis always having that equal sign. Okay, so that is the null hypothesis in all of these situations, just that there actually is no difference. They're just equal. Okay, and now for the alternative hypothesis, we want to think about, okay, what is the actual claim going on here? So a study is done to determine if company A retains its workers longer. So I would say for the alternative hypothesis, we're interested in company A, which I called mu number 1. We want to see if that is larger retainment than the mu 2, which was what I labeled as company B. Okay, so that tells me that it is a right-tailed test. Okay, and so if you wanted to use subscripts of like A and B on those mu's, then that's okay too. We would just have mu sub A is greater than mu sub B. Okay, but I'm going to use those subscripts of 1 and 2. All right. Now let's go ahead and compute that test statistic. So I want to leave myself some space because the degrees of freedom is actually going to take some space. So I'm going to write the test statistic right here. I'm going to start it right here. The test statistic. Okay, and I'll use that little subscript of a 0. You don't need to use little subscript of that 0. You can just write t equals, but I'm going to use the subscript 0 just to differentiate it from any other t scores that I might write down later. So let's just write down the whole formula. And so the whole formula is x1 bar minus x2 bar minus mu1 minus mu2 divided by big square root here, the standard deviation squared of sample 1 divided by its sample size, plus the standard deviation squared of sample 2 divided by its sample size. Okay, and when I say standard deviation squared, that really just means variance, but I'm going to think about it at like standard deviation squared because we were given standard deviations. So we're going to need to square those. Okay, so as we go ahead and plug this in, it's really important to note that with that null hypothesis right here, with this assumption about the population means, with mu1 equals mu2, that's actually the same if I would like subtract mu2 from both sides. That's exactly the same as mu1 minus mu2 equals 0. Okay, so for these situations, we're assuming with that null hypothesis that the difference between mu1 and mu2 is 0. And so that's actually nice because if we go over to our test statistic, this part right here with mu1 minus mu2 as the theorized difference in the population means, this whole part is just going to be a 0. So we don't even need to worry about it. Okay, in some scenarios, there are hypothesis tests where you might be trying to test to see if there is some difference that's not a 0. Maybe you're trying to test to see if the difference is 1 or 2 or 5 or whatever. But here we're just assuming that that null hypothesis is the difference is 0, meaning that the population means are equal. Okay, so that will always be the case for this class. All right, so that's kind of nice. It simplifies the work a little bit. So let's go ahead and start plugging all these pieces in. So x1 bar, so we have 5 minus x2 bar, that is 4.5 divided by, okay, so down here it's going to be a little bit of a mess. And as I type it into my calculator, I'll probably want to do like maybe one step at a time so we don't get lost. It's really easy to type it in incorrectly. So S1 squared, that's going to be 1.2 squared divided by its sample size is 15 plus S2 squared, so that's the 0.8 squared divided by its sample size, which was 20. Okay. So on top, I'm going to just do this separately on my calculator so that we don't get all like out of control here. So 5 minus 4.5. So in the numerator, that's 0.5. And then in the denominator, I'm going to leave the square root symbol over it and just calculate the 1.2 squared divided by 15 plus 0.8 squared divided by 20. And I'm getting 0.128. Okay, and then now I'm going to go ahead and type that all into my calculator, 0.5 divided by square root 0.128. And so I'm going to go a few decimal places, 1.3975. All right, there is our test statistic. Okay, now, if this was a z-test, then we're ready to dive right in. But because this is a t-test, we need to calculate that degrees of freedom. And in the past, it was just one less than the sample size. But because we've got two different samples, it ends up being much more complicated. So I'm going to calculate that degrees of freedom by hand. But in the future, we're probably not going to do this unless you want to. Okay, so let's do the degrees of freedom by hand. So I'm going to say degrees of freedom. Okay, so df equals, so I'll write down the whole formula again. So I've got it on my paper right here, so I'm not going to scroll back up there. But the degrees of freedom, it's S1 squared over N1 plus S2 squared over N2. All that needs to be squared. Big fraction here, and then we have S1 squared over N1, and all of that needs to be squared and divided by N1 minus 1 plus S2 squared over N2, and then all of that gets squared. And this is all over N2 minus 1. Okay, so crazy formula there. I'm actually not quite sure where that comes from, but with my studies of statistics in grad school, a lot of these formulas, I remember they're derived using nice calculus techniques to like minimize error terms and all kinds of cool stuff. Okay, so we're certainly not going to prove that formula or anything. We just get to use it. Okay, so let's plug in all of the pieces of information, and I'll probably go step by step just to make sure that we don't make any mistakes typing this into our calculator. So for the S1 squared, so let's go, that's 1.2 squared divided by N1 is 15 plus S2 squared, that's the 0.8 squared divided by N2 is 20. And all of that gets squared. Okay, and now S1 squared again, so kind of repetitive seeming. So we've got the 1.2 squared over 15 for its sample size, and all that gets squared. And then down here, N1 minus 1, that's 15 minus 1. Plus, okay, we've got the 0.8 squared divided by the N2 sample size, and square all of that. And then N2 minus 1 is 20 minus 1. Okay, so I'll go little piece by little piece. So I'll start off by just doing the inside right there. So 1.2 squared divided by 15 plus 0.8 squared divided by 20. And so I got on the top there, I'm getting 0.128, and that still needs to be squared. If you want to type everything all in at once, go ahead, but I don't really recommend it. There's a lot of stuff to keep track of here. Okay, so I'll do each one of these pieces maybe separately down here. So the 1.2 squared over 15. And so that part becomes 0.096. I didn't square that yet. And then on the bottom there with the 15 minus 1, I can write that as 14. Okay, so I just did the inside the parentheses part right here. And let's do the other one. So the 0.8 squared and then divided by 20. And I'm getting 0.0 0.032. Okay, and that's squared and divided by 20 minus 1 is 19. Okay. Now in the top, we can go ahead and do the 0.128 squared, and I don't want to do any rounding until the very end, so that's 0.01638 divided by, okay, so I'm going to go ahead and type both of those pieces in. So the 0.096 squared divided by 14 plus 0.032 squared divided by 19. And I'm getting, it's showing the scientific notation with the little e-4. So that means I need 3 extra zeros to the left of this 7. So I need 0.123. And then I'll write a few of these digits, 7, 1, 2, 1, 8. All right, and then finally, I'll do that numerator divided by that denominator. And what are we getting? And I want to round to a few decimal places. I'm getting 23.0054. All right. There are the degrees of freedom. Okay, so I'll make a little note to myself. Those are the degrees of freedom. And then this was the, that was the test statistic. All right, so yeah, definitely a pain to calculate the degrees of freedom there. 2 samples combined into 1 sort of. All right, so with the degrees of freedom though, and that test statistic, the rest of this ends up being just like kind of like a standard t-test. Okay, so the hardest part, in my opinion, is just calculating those 2. Okay, but now we can proceed and it's going to seem very, very familiar. So I'm going to do the classical approach. And I'll also do the p-value approach. All right, so with the classical approach, if you recall, it's a t-distribution, so it still looks like that symmetric bell curve. And then we had an alpha of, I believe it was 0.05. Yes, okay, so alpha equals 0.05. And we had a right-tailed test. So I'll go ahead and set up a right-tailed test with the critical region shaded in on the right-hand side. And we're going to get a t equals, which we don't know yet. We want to find out what that critical value is. For alpha equals 0.05, remember that this is going to equal the area in 1 tail. Okay, from our table of t-scores, remember that it really only gives you the positive version of your t-value. So we just want the 1 tail, okay, rather than the 2 tail. Okay, but that degrees of freedom that we calculated so dramatically over there, 23.0054. And as long as you have that degrees of freedom, which in my opinion is the hardest part of this whole process, we're good to go. The rest of it is very familiar of what we've done before. So this t, we want a critical value. Okay, so that'll be the critical value. And then recall that this side over here is called the critical region. Okay, so let's use our table to find out what the critical value would be if we've got 0.05 area in 1 tail with 23.0054 degrees of freedom. Well, the table doesn't go into decimal degrees of freedom, so 23 is close enough. Okay, so let's pull up that table. And so we need to do the area in 1 tail of 0.05. So I need to do this column right here. Okay, and 23 degrees of freedom. So I'll scroll down to the 23 degrees of freedom. And so this is the closest that the table can get for us for a critical value. So 1.714. Okay, so let's write that down. That's the critical value. t equals 1.714. Okay, and now if you recall, we just want to see where does the test statistic lie. And so that test statistic that we had was 1.3975. Okay, so I'll do that same thing that I did. Well, I'll use a different color here. So for the red right here, 1.39 compared to 1.7, 1.7 is bigger. So the test statistic, I'll just put a little dot right here. Right there, the test statistic of T naught equals 1.3975 is not in the critical region. Not. Okay, so then what does that mean? If you recall, the test stat not in the critical region means that we do not reject the null hypothesis. So not in the critical region means not reject. Okay, so we have our decision right there already, but like I said, p-value moving forward, the p-value method is going to be the preferred method. And the homework problems are typically going to ask you for a precise p-value, which we're going to need some form of technology to get. Okay, but let's go ahead and work out that p-value method and make sure that we get the same decision. Okay, so for the p-value method, it's still going to be this right-tailed test. We use that test statistic right here. Okay, so the test statistic of the 1.3975. Okay, and then this area right here to the right, that is exactly the p-value. Okay, so right in there, it's the area in one tail is going to equal the p-value. Okay, and we still need to be considering that degrees of freedom of the 23.0054. Okay, so let's go back to our table, and the table is just going to give a p-value in between two values most likely, so I'm definitely going to pull up a couple forms of technology to find that precise p-value. But degrees of freedom 23, and then we just need to find the area in one tail that would correspond to this t-score, so 1.3975. If we go to the table, if we go into the 23 degrees of freedom, if I want to find right in here where the t-value is, 1.3975. So 1.3975 looks like it's between these two. Would you agree with that? Okay, 1.3975. Yeah, so it's got to be in between these two. And so because it's in between those two, I have to go up and see what is the one tail area. It's between 0.05 and 0.10. That's the best that this table can do, which is not good enough to answer our homework questions. It's good enough to answer the whole hypothesis test, but the homework wants specific p-values. So anyways, I'm going to write that down as it's between 0.05 and 0.10. So the p-value using the table, the p-value is between 0.05 and 0.10. And like I said, that's actually enough to answer the question or to make our decision, because if the p-value is between 0.05 and 0.10, then that means it's larger than 0.05. And remember that the alpha was 0.05. Okay, so it's somewhere larger than 0.05. So we know that the p-value is greater than alpha, which is bad. Okay, that means we do not reject the null hypothesis. Okay, but for tech, this is important, the tech p-value equals. Okay, so let's find that tech p-value, and so I'll do it in a couple of different ways. I'll use the graphing calculator first, and then I'll use the online p-value calculator. Okay, so for the tech p-value, we just want to get the area to the right with this t-score as the lower bound. Okay, so if you recall, let's go to the calculator, and we want the distributions here. So I'm going to go second vars, and we want the t distribution, and I want the cumulative t distribution. So TCDF, the t cumulative distribution function. Okay, for the lower, I want that critical value. And so 1.3975. 1.3975. Okay, for the upper, I just want it to be infinity, so you can put that as 10 to the 99. For the degrees of freedom, we had the 23, and we can actually get more precise with our calculator, so I can actually type in 23.0054. I don't think it'll make much of a difference, but 23.0054. Okay, and let's paste that onto our screen and press enter. And so here is the more precise p-value that we would use to enter into like our homework problems. So let's write that down. It's 0.08779. I'll go several decimal places just so that we can make it crazy accurate. Okay, so I'll write down several of those decimal places. 0.08798. Okay, so there is the p-value. You might need to round that to 2 decimal places or 3 decimal places or 4 decimal places, whatever you're being asked for. But there is the tech p-value. Okay, let's go ahead and confirm that because I've got this nice p-value calculator right here. So let's click on that if you're not using the graphing calculator. And then I like this one because as long as you've got your t-score or your z-score, you're good to go. Okay, and you also need your degrees of freedom for the t-score. So let's click on the t-score p-value. Okay, and our t-score was the 1.3975. 1.3975. And the degrees of freedom, which was definitely a hassle to calculate, that was the 23.005. And it won't let me go any more decimal places than that. Okay, so that's plenty. The significance level is 0.05, so I'll leave that checked. We are doing a one-tailed, okay, it's right-tailed, but just keep it as one-tailed and click calculate. Okay, so it tells us that the p-value is 0.087798. And I believe that's what we wrote, 0.08779. Okay, so that's the same that our calculator gave us. So that's excellent. And then like our decision, the result is not significant because the P is less than, it's not significant with the p-value being less than the 0.05. Okay, so like we said over here, and I like to word it, I like the way we word it better. The p-value is greater than that 0.05. Okay, so that p-value is 0.08. So the table was right. That number is between 0.05 and 0.10, and that was enough to make our decision. But yeah, we want accurate p-values, and so I'm probably going to be recommending that you find that exact p-value from now on, okay, if you're not already doing that. Okay, so yeah, we do not reject the null hypothesis because that p-value is bigger than alpha. Okay, so let's write our conclusion, and then I will show you the full hypothesis test version that does a lot of this for us. Okay, so the conclusion here. So at the 5% significance level, okay, so at the 5% significance level, there is not sufficient evidence from the sample data to support the claim. Okay, and after all of this work, what were we actually testing? Okay, so going back up here, remember that we were just testing to see if company A retains its workers longer than company B. Okay, and we were not able to reject the null hypothesis, so we were not able to support that claim. Okay, so there is not sufficient evidence from the sample data to support the claim that company A retains its workers longer than company B. All right. So let's go ahead and use the technology version, which is something that I recommend that you try out and starting to move more and more towards using technology because I certainly don't want to have to calculate that degrees of freedom by hand every time. That sucks. Okay, so let's go ahead and use the technology here. And so I've got this link. There's other links, or there's other places that you can get this with a Google search, but I included one that's pretty reliable right here with LibreText. And so this one says right here, it's a 2 independent sample with statistics. Okay, so we have our independent samples and the statistics were given to us, meaning all of the sample statistics were given to us. So let's enter all of the pieces of information. And so for this first sample in company A, the sample size was 15. So I've got it written on my page here, but I want to make sure that you're in agreement. Okay, so we want to just enter all of this information right here. Okay, so the sample size for company A, so I called this sample number 1, that was 15. The sample mean for that one was 5. The sample standard deviation for that one was 1.2. Okay, the second sample, the size was 20. The sample mean was 4.5. The sample standard deviation was 0.8. Okay, then you got to click on which type of test we're doing, and we were doing a right-tailed test, so I'm going to click the greater than symbol. We can enter the confidence level here, but that's really only for dealing with, I think this also generates like confidence intervals or something, which I'm not using right now. But we do have to be a little bit careful because we use alpha is 0.05, but they want us to enter it in terms of the confidence level rather than the significance level. Okay, so it's kind of tricky there, but we're not even actually using that part. But if we wanted to, alpha being 0.05 means that the confidence level is 0.95. Okay, but that's actually not important because we don't care about these lower bound, upper bound stuff. I'm interested in the T and the P. Okay, so let's calculate, and here are the T-score. That's the test statistic, so 1.3975, so all that work that we did to get that 1.3975, that's the test statistic. And the p-value right there. So all of that work that we had to do getting the degrees of freedom in order to be able to calculate that p-value in the first place, there it is, just the p-value. So we don't know the degrees of freedom, but we do know the p-value, 0.08779, and that's matching up with our p-value 0.08779. Yeah, okay, so dang close enough out to several decimal places. Okay, and then let's also look at the calculator. Okay, so anyways, I mean, this is an excellent way to confirm your work, or to even, I'm okay with skipping some of the steps. Like, I'm not going to expect you to calculate the degrees of freedom by hand unless you want to be able to use the specific degrees of freedom so that you can actually start using that cumulative distribution function, because we did need to enter the degrees of freedom there. Okay, so suppose that you didn't want to do the degrees of freedom here and you wanted to use your calculator. Let's go ahead and do it. I would click on Stat for full statistics tests, and I go over to tests. And right now we are doing a 2-sample t-test. So I want to highlight that one and click Enter. Okay, there's the 2 options for data, which is with if you've got like 2 different columns of raw data. And so I would click on data, but we don't have that. We have our actual stats given to us about the data. So I want to make sure I highlight stats there. And then I just go ahead and enter all of the information. So X1 bar, that's the sample mean for sample number 1. And so that was 5. SX1, that's the sample standard deviation for sample number 1, and that was 1.2. N1 was the sample size for sample 1, that was 15. Okay, X2 bar, that was 4.5. So I'm just entering the information, being careful about what's what. SX2, that's the sample standard deviation for sample 2. And N2 was the sample size 20. Okay, select the correct alternative hypothesis. So we had mu1 greater than mu2. So that is the right-tailed test there. Make sure you leave pooled as no. Okay, we're leaving these as no for pooled, and don't worry about what that means. Just go ahead and leave it as a no, and then you can click on calculate. And there is the test statistic, the 1.3975 that we calculated. There is the p-value, 0.8779. Okay, and then maybe it starts getting different way out in like 5 or 6 decimal places, but we're typically rounding to like maybe 3 or 4 decimal places for the p-value. It does tell us that degrees of freedom. Okay, so the online calculator did not do that, but this one gives us that nasty 23.0054 number for the degrees of freedom. But anyways, we're mostly just interested in the t, the p, and the degrees of freedom if you wish. Okay, so lots of different information there on how to get all of this stuff. Like I said, I want to start moving more towards using technology rather than the classical approach and using the tables. Okay, so I'm going to just focus on kind of using technology and the p-value approach moving into example 3. All right, so stick around for that.